Science fiction writers, 10-year-old boys, and many of the innumerable crackpots who send me their theories of the universe each year are united by one conviction: that things can travel faster than the speed of light. In fact, relativity does not impose c as an absolute speed limit, but it does spell out the consequences if that limit is exceeded. After this lecture, it will be up to you to decide if you're willing to live with those consequences. Science fiction writers and 10-year-old boys also love antimatter, but that's just fine, because antimatter really exists. Indeed, as I explained way back in Lecture 2, every particle in the putatively fundamental list of particles, the 6 quarks, up, down, strange charm, top, bottom, and the 6 leptons, muon, tau, electron, and their relevant neutrinos, each has an antimatter mate. This is not just theory. We can make and we can detect each of these antimatter particles: antimuons, antiprotons, antineutrons, antineutrinos. The anti-electron, or positron as we've called it, is the instigator of half of all radioactive beta decays. The positron's emergence from the nucleus signals the transformation of a proton into a neutron and the demotion of that element one step in the periodic table. Antimatter is frequently produced in the cosmic ray collisions with the air we've discussed. And as we shall see, antimatter played an absolutely crucial role in the first moments of the universe, when all matter was born. Relativity theory is the theory that allows us to explain both the consequences of faster-than-light travel and the mechanism by which antimatter arises. We'll begin with the former, since it is important for deepening our understanding of space and time. And we'll end with the latter because it plays such a central role in the early days of the universe, when the building blocks of our atomic historians were created. Let's start with the challenge I offered a couple of lectures ago: define time. Not only does subjective time that we experience in our lives flow at different rates, we have seen that relativity tells us that even objective time, kept by accurate clocks, runs at rates dependent on one's velocity. My old cosmology professor, Ted Harrison, had a good metaphor for time, although I'm not sure I'd endow it with the definition. He called time a wave of vividity. And he drew it like this. At the moment we are now, our vividness is at a peak. I vividly feel the lights on my face, the pencil in my hand, the paper under my other hand. The moment is vivid. A minute ago, things were almost equally vivid. I was standing here talking into the same cameras with the same lights and the same paper and the same pencil in my hand. Yesterday, well, that's a little less vivid. I don't remember exactly what I was doing at this time yesterday. A year ago, I certainly don't remember precisely what I was doing, so the vividity index falls off and generally slopes away to close to zero. I certainly don't remember what I was doing when I was 2 years old. There are little peaks occasionally. For example, it's still very vivid to me the time when the zipper on my jacket got stuck in first grade and the teacher had to rip it off over my head, including taking with it my shirt, such that I was standing half naked in front of my first grade compatriots. So there are vivid moments like that. The wave of vividity also extends a little bit into the future sometimes. If I step off the curve in New York without looking and turn to the left and see a bus only 2 meters away, it's very vivid to me what's about to happen. Still, this is a nice analogy for time, but it's not a definition of time. We agree that time and space are not absolutes anymore once we adopt the theory of relativity. Is there anything that all observers can agree on? They can't agree on time. It runs at different rates. They can't agree on simultaneity. They can't agree on distances. They can't agree on masses. Is there something that's absolute and invariant for all observers? The Greeks recognized that one could calculate the distance between 2 points on a 2-dimensional plane using the Pythagorean theorem. You have a coordinate system with an origin, you have an x value and a y value, you plot the point at that location, and you draw a line. If you take x squared plus y squared, it's equal to the distance d squared between the 2 points. The 17th century mathematician René Descartes generalized this to a 3-dimensional world, the one in which we live. If you draw a three-dimensional graph on the piece of paper and plot a point at some position x, y, and z in or out of the page, then the distance from the origin to that point, d squared, is simply given by x squared plus y squared plus z squared. Einstein now has generalized space and time into a four-dimensional space-time. One might expect, in this case, that the space-time interval, d, will be given by d squared equals x squared plus y squared plus z squared plus t squared. But as usual in relativity, one's common sense notions are incorrect. In fact, in relativity, the space-time interval, the distance between 2 points in the four-dimensional space-time, d squared, is equal to time squared minus space squared, where space here is meant to stand for the three normal dimensions, x, y, and z, and where the minus sign is an indication of the bizarre properties that space-time has. This space-time interval, d, defined in this way, is in fact invariant. All observers will always agree on this interval between 2 points in space-time. They disagree, as I've said, on lengths in space and intervals of time. They disagree on whether or not two events are simultaneous, but everyone agrees on d. It will turn out that the shortest distance, the shortest space-time interval between 2 points, is not a straight line, yet another bizarreness of relativity. To represent space-time, we simply draw what we call a space-time diagram, with one dimension of space, usually that on the x-axis, and one dimension of time, which we draw on the y-axis. Now, in reality, we would try to represent the full 4 dimensions, but I have trouble even drawing three-dimensional figures on a two-dimensional piece of paper, so let's stick to the one x dimension for now as representing the dimension through space, and the y-axis being the dimension through time. To make this easy to interpret, we label the axes such that the time axis, say, is labeled in seconds, and the x-axis is labeled in light seconds, that is, the distance light travels in 1 second. Or, if we're talking about events out in the universe, we might label the y-axis in years and the x-axis in light years, the distance light travels in a year. This diagram is made up of many, many events. A point in this diagram represents an event because it is something that happens at some particular place in space at some particular moment in time. The place in space is located on the x-axis, the place in time is located up the y-axis, and a point there represents the event. An object sitting still in a space-time diagram is represented by a straight vertical line, because time is certainly passing for that object, but it's not moving anywhere in space. We call this a world line. An object traveling from one point to another at a constant speed in the space-time diagram looks like a tilted world line because it is moving through space, so along the x-axis, as time passes. So it makes it a tilted line. Accelerating objects are a curved line. They start off standing still, so a vertical line, and then they gradually tilt away more and more and more as they cover more space in a given amount of time. Light has a very special place in the space-time diagram. With the axes labeled conventionally, since light travels 1 light second in 1 second, 2 light seconds in 2 seconds, light will be represented by lines at 45 degrees, covering 1 light second in 1 second, 2 light seconds in 2 seconds. Drawing the two diagonal lines from a given location forms what we call the light cone, because it looks sort of like a cone. The light cone divides the diagram into a time-like part containing an absolute past and an absolute future, and a space-like part which is at present unreachable by the observer at the point where the lines cross, and contains relative past and future. For example, if you're sitting here at the origin of these two 45-degree lines, anything in the backwards part of your light cone you've already seen, because light from any point, any event, an explosion, a birth, a death, in that back light cone, the light will have had time to reach to you, and you will already know about it. The things in the forward part of the light cone, you absolutely have not got to yet. An event happening there will not come into your ken until you reach that point in the diagram. But an event that happens outside of the light cone is neither in your past or your future, or rather, it could be both in your past and in your future. It could be in your past in the sense that if you drew a line horizontal across the diagram from where you are today, you might think everything below that is in the past. But as I discussed in talking about Betelgeuse, the star in Orion that's about to explode, if the star is 400 light years away and it exploded 300 years ago, we won't know about it yet, because it will lie outside of our backwards light cone. Only as we move forward in time and our light cone encompasses more and more and more of the space-time diagram will the supernova eventually come into view. The invariant space-time intervals d reveal interesting aspects of the diagram and of reality. The longest space-time interval between points A and B on a stationary world line, that is, a vertical line, is that distance, the straight line that connects points A and B. Because d squared is time squared minus space squared. And the space motion in that case is 0. You're in the same place. You're at the same point on the x-axis. So t squared minus 0 is the maximum amount that you can get. A shorter interval would be obtained by traveling away from the location and then returning again, because the same amount of time has gone by, but you get to subtract off the space through which you've traveled. We'll see how this works in a moment. We actually saw this effect when discussing the atmospheric muons last time. Let's see what that situation looks like on a space-time diagram. From our perspective, the muon has to travel a long way through space, from the top of the atmosphere over here on the x-axis to the Earth over here on the x-axis. Now it's traveling very close to the speed of light, so it's almost at a 45-degree angle. What kind of space-time interval does it go through? Well, it goes through that amount of space and that amount of time, d squared equals t squared minus x squared, and you see it's a very small space-time interval which it's gone through. It looks like a long time to us to get there. That's its moving clock running 100 times slower than normal. But in space-time, it's a very short distance. From the muon's perspective, it sees the Earth rushing upon it as soon as it's created, and a tiny interval later slamming into it. It lives what it thinks is a normal amount of time, a small amount on the time axis. But that's okay, because it doesn't have very far to go. The space-time diagram shows how the unusual situations, the non-commonsensical situations of relativity, are easily explained. The property of space-time represented by this effect gives rise to the famous twin paradox. Suppose you have a twin who becomes an astronomer, an adventuresome type who decides to go off on an interstellar journey. You'd rather stay at home and watch teaching company DVDs. So here's you on the diagram, staying at home in the same place as Earth as a vertical line. And here's your twin that goes accelerating away and then cruising at nearly the speed of light, off perhaps to see whether Betelgeuse is really going to explode soon. He gets there, takes his measurements, decides that an explosion is imminent, and promptly turns around to return and alert the astronomers on Earth so they'll be ready for this monumental event. Tragically, when he arrives back home, he finds two things have happened. First, everyone already knows the star has exploded, and second, his twin is dead. Let's analyze this scenario on the space-time diagram. Because we're talking about traveling hundreds of light years through space, we'll label the x-axis in light years and the y-axis in years. Now, here's you, your vertical word line indicating that you're sitting still on the Earth. And here's the path of your twin's trip out to the vicinity of Betelgeuse and then back again. What happened? After he started his return, the star exploded. And while he was traveling fast, the light from the explosion traveled precisely at the speed of light, spreading out in all directions, and in particular moving towards Earth at light speed, faster than his rocket could travel. Obviously, then, it arrived before he did, so the explosion was old news by the time he returned. In addition, we must calculate the space-time intervals represented by your journey through space-time and his. Your journey, sitting there watching the DVDs, is given by d squared equals t squared minus x squared, and since the space you covered was limited to that between your couch and the refrigerator, it's essentially t squared, because the space squared is 0, especially on this diagram where the x-axis is labeled in light years, 1 light year being 6 trillion miles. In this scenario, 801 years has gone by since your twin left on his journey. It's very likely, I'm afraid, that your personal world line will end before 801 years is up. Your twin, however, will have covered a distance d squared equals t squared minus x squared, but in his case, x squared is a very big number. He's gone 400 light years out and 400 light years back. If, for example, he were traveling at 99.9% the speed of light throughout most of his journey, the space-time interval through which he has traveled, going from the time he left to the time he returns at Earth, is only 36 years. So he'll be a little older, but just fine, there to meet your great-great-great-great-great-great-great-great-grandchildren. But wait, you should be saying, I thought you said last time that the situation was symmetrical. I see his clock running slow because he's moving, but he should see my clock running slow too, so why aren't I here to greet him? Well, remember the conditions of Einstein's postulates. They hold in situations where velocities are constant. Clearly, if you accelerate from Earth to nearly the speed of light, go out to Betelgeuse, turn around, and come back, your velocity isn't constant. I've slipped a new condition into the story. Accelerations are involved. These accelerations and decelerations, when he turns around at Betelgeuse, violate the strict conditions in which special relativity applies. General relativity, which took Einstein another 11 years to figure out, takes care of this, so the situation I've described would occur the way it does, but the simple equations of the relativistic transformations I've taught you don't really take that into account. The special role of light is apparent on a space-time diagram. The space-time interval experienced by a photon, d squared, moving from here to here on the diagram, is 0, because it's the time squared minus the space squared. And since by definition this is a 45-degree line, those two distances are equal. T squared minus x squared equals 0. Light does not experience space-time. The photons we will meet, which come to us from the very edge of space and time, haven't gotten tired along their 13.7 billion year journey. No time has elapsed for them at all. Now, different observers draw different space-time diagrams because each observer believes he or she is sitting still and is therefore represented by a vertical line. The lines of one observer traveling with respect to the other will be tilted with respect to each other. We just take the whole graph and rotate it, since each observer thinks he or she is stationary. However, most importantly, the light cones on these tilted space-time diagrams do not tilt, because the speed of light, according to Einstein's second postulate, is constant for all observers. Space-time diagrams make it easy to illustrate the consequences of faster-than-light travel, the first of the two keys of relativity I want to talk about today. Consider a scene in which you're standing in a room, looking out the window, and see a nasty little kid pick up a rock and hurl it at the window. So, space-time diagram, we draw t on the y-axis, space, x, on the x-axis. We draw a vertical line for your world line, a vertical line near you representing the window, and a vertical line farther away representing the kid who picks up the rock. The sequence of events that you see is clear. The kid first picks up the rock, then you see the kid throw the rock. These are all represented by light cones on the diagram as time moves forward. And then you see the rock hit the window, and then you see the window break. It's only common sense. Now, imagine instead this is a high-tech kid that has a laser gun instead of a low-tech rock. His aim is the same, to break your window. Let's plot what you would see in a space-time diagram in this scenario. Well, the kid is born down here sometime. He grows up. He enters your past light cone, so you know of his birth. The kid picks up his laser gun, and he fires the laser gun. The laser, of course, is just light, so it travels along the light cone. From your perspective, it A, leaves the gun, B, hits the window, and C, you see it simultaneously because it travels at the speed of light, and that you can't see anything that happens before the light manages to reach you. Now, this does not mean that light takes no time to travel this distance through space. Light has a finite velocity, 300,000 kilometers per second. And so, velocity equals distance over time. That means time equals distance over velocity, d over 300,000 kilometers a second. That's a real number. It takes a finite amount of time for the light to get from the laser gun to your window. However, it does mean that the light does not experience spacetime. Its spacetime interval is 0, and it means you do not see a gap between the time when the gun is fired, the window breaks, and that information reaches your eyes. The gun really did fire before the laser beam got to the window, but you cannot observe that because you can only observe the light. Now, here's the challenge for you faster-than-light people. Consider that the kid, rather than a rock or a laser, has a hyperrock that can travel faster than the speed of light. Again, we draw the space-time diagram. Time on the y-axis, space on the x-axis, the vertical line for you, the vertical line for the window out which you are observing the scene. The sequence of events, if we draw the kid and the hyperrock in this way, comes to you as follows. The window breaks, the kid is born, and then he throws the rock. Now, this situation is not forbidden by the laws of relativity. Indeed, my late colleague Gary Feinberg invented tachyons, theoretical particles that behaved like hyperrocks. They go faster than the speed of light. And Gary worked out all their properties. They're a little bit strange. They travel backwards in time, they have negative energy, etc. Gary was a connoisseur of science fiction and would not be unhappy to see today that his tachyons have gained life in popular literature, although he certainly didn't expect that their presence would ever be discovered in the real universe. Because traveling faster than light eliminates cause and effect. It is not forbidden by relativity. Relativity has nothing to say on the subject except to allow one to compute the properties of entities that travel faster than the speed of light. The price for allowing it, however, is abandoned cause and effect, all ye who enter here. As a brief aside, I should note that it is the speed of light in the vacuum of space that no object with mass can match. Light actually travels more slowly through matter, through air, through glass, through water, and it is possible for particles in air to exceed the speed of light in air, although not the 300,000 kilometer per second limit. Indeed, we actually observe particles traveling through air faster than light travels through air. When they do, they emit a ghostly little blue light, which is called Cherenkov radiation. And we've actually detected this signal in our atmosphere with telescopes, where the signal is produced by high-energy cosmic rays that we keep discussing that slam into the atmosphere and make the radioactive isotopes and muons that we've discussed. While travel faster than light in a vacuum is not happening, antimatter is another matter, so to speak. One of its most bizarre properties is that it disappears when it encounters normal matter. Now, I mean disappears completely. Its mass no longer exists. This would seem to violate the law of conservation of mass, that pillar of 19th century science that was so central in the development of both chemistry and of physics. And indeed, it does violate that law. You start out with a proton and an antiproton. Both of them are perfectly well-defined objects. They both have mass. You can put them on a scale. They weigh 1.67 times 10 to the minus 24 grams. Yes, it's a small number, but that's okay. They have mass. You can record it. You bring them together, you end up with 0. M equals 0, precisely. Again, relativity comes to the rescue to explain this circumstance. Yet another consequence of Einstein's two postulates and the redefinition of time and distance they require is that mass is not constant either. As we saw last time, in the relativistic transformation, mass is one of those relative properties which depends on the speed of the observer. M prime equals m divided by the famous square root of 1 minus u squared over c squared. Pixel on the train looks even fatter than he does in reality to me standing on the ground. This notion alone already does violence to the idea of conservation of mass. But the full implications of the theory of relativity go well beyond this. By following the logical consequences of relative times, distances, velocities, and masses, and developing additional such concepts like relativistic momentum and rest mass energy, but without involving any terribly complicated mathematics, one reaches a remarkable conclusion: that mass and energy are equivalent quantities, that you can convert one to the other as long as the total of the two is constant. The famous expression of this equivalence, perhaps the most famous equation of all time, is E equals mc squared. E is the total energy, m is the mass, and the proportionality constant between them is c. Unsurprisingly, that speed of light again, which keeps showing up everywhere, the speed of light squared. If one has a photon, the ultimate expression of pure energy, absolutely zero mass, it can spontaneously, if it has enough of that energy, turn itself into a particle-antiparticle pair, both members of which do have mass. You can catch them, you can put them on a scale, and you can weigh them. Symmetrically, any antiparticle-particle pair that meets up will quickly annihilate, their masses disappearing completely into the energy of a photon that speeds away, obviously, exactly at the speed of light. Einstein's relativity provides yet another example of how, on scales with which we cannot be intimately familiar, in realms far from the direct experience of our senses, things can be very different than they are in our prosaic world of human scales. Having yet to discover tachyons, we must rely on photons, traveling merely at the speed of light, to bring us information about the most distant reaches of space, and therefore of time. In particular, we are now prepared to examine the oldest photons in the universe, the afterglow of matter-antimatter annihilation in the Big Bang itself, in order that we may complete our history of the atoms and their constituents.